Okay, so we need to talk about something that's called oxidation states. Actually, oxidation states and oxidation numbers. But oxidation numbers are just the numbers we assign to the states. So really, the physicist in me wants to say they're the same thing. But if there was a chemist in the room with me, they'd be like, no, there's a difference. So I'll try to distinguish the difference for you. So really, an oxidation state is the apparent net electric charge that an atom would have if the electron pair in a covalent bond belonged entirely to the one that was more electronegative. Okay, so what does that mean in English? Okay, well, you know that like in compounds like water, H2O, that these guys share a pair of electrons. In each of these covalent bonds, there's a pair of electrons that are shared. So the oxidation state of hydrogen and the oxidation state of oxygen would be dependent on which one of them wins the tug of war in that covalent bond, which one has the electron pair closer to it. Well, and the way we figure it out is we look at the electronegativity of the atom. And I'm thinking you would have learned about this in chemistry. Okay, so if you go to your periodic table, you will see on this little chart that the number right under the atomic number is the electronegativity. The electronegativity really tells us about how much this particular atom wants to hold on to that electron, how desperately it wants it. If you think back to physics when we were talking about what makes up a metal, and I was saying like the ones over here desperately want an electron, so it shouldn't surprise you that fluorine has the highest electronegativity. Oxygen has a really high electronegativity. So does chlorine. So does nitrogen. And then as we move away from this corner, and you'll see these noble gases, they don't have an electronegativity at all. They have a full outer shell. They don't need to try to steal an electron. But fluorine, chlorine, they desperately want an electron. Now, if we look at the opposite side, you will see they're really low over here. These guys don't have a huge hold on their electrons. Sorry, I'm trying to blow it up and make it clear, and it's just not happening. Because they have that one in the outer shell that they don't care about, right? So their electronegativity is a lot less. So if we go back then to the definition of an oxidation state, it's the apparent electric charge on an atom, or that an atom would have, depending on which one pulls this pair of electrons in the covalent bond, which one pulls it more. So if we look at oxygen's electronegativity is, I have to bring it up here so I can see it, 3.4, and hydrogen's is 2.2. So oxygen's going to win. So oxygen's going to end up having an oxidation number of -2, whereas each of the hydrogens is going to end up having an oxidation number of +1. Now, it's not really true because they're sharing it, but we're assigning the electron to the one that has the higher electronegativity because we're saying, okay, so this electron pair is going to be closer to these ones. So oxygen's going to end up with a -2. Hydrogen's going to be like it's missing one. Okay? So it doesn't necessarily represent the charge. Now it could if we're talking ions, but it definitely doesn't when we're in covalent bonds. Okay? So the oxidation state doesn't necessarily represent the charge. They're really like the imaginary charge, the charge that they would have if they could take these electrons completely. The concept is somewhat arbitrary because it's based on assigning charges, not real charges. But it's all, if you do it, it's always, if you are self-consistent with it, then it's helpful for the prediction of electron transfer. Okay, so that's oxidation states. Oxidation numbers then are just the numbers like we applied. They're the numbers that are assigned based on the state. Okay, So these are the oxidation numbers once we figured out that the state would be that these electron pairs would be closer to the oxygen than the hydrogen. All right, so now there are some rules of how we do this, okay? And they're in that little chart if you have your page of notes there. So the first rule is that all atoms that are elements, all atoms that are in their pure state, their oxidation state is 0. Okay, so if it's like pure copper, if it's H2 gas, if it's pure sodium, pure chlorine, Cl2, whenever they're in their pure state, okay, so here we go, Cl2 gas, that's pure, Fe solid, Cu solid, all of these guys, their oxidation state is going to be 0, okay? Hydrogen, most often, hydrogen in compounds, hydrogen will be a positive 1. Okay? Most often, oxygen in compounds will be a negative 2. So the two of them will act the way they usually do when they're ions. All ions, all monoatomic. Okay, so not the polyatomic, but all the monoatomic ions will have an oxidation number that will match their charge. So H positive again will be a positive 1. Ca2 positive, it'll be a plus 2. Okay? So those are the basic rules, that all the pure guys will be 0, hydrogen in any compounds will be positive 1, oxygen in any compounds, negative 2, and all monatomic ions will have the charge of the ion. But like all rules, there are exceptions. And the exceptions are really dealing with hydrogen and oxygen. Hydrogen first. Hydrogen will have an oxidation number of negative 1 instead of positive 1 whenever it's bonded to a less electronegative element. So you have to go back to the table. Whenever hydrogen is bonded with something that has an electronegativity less than itself, like lithium does, like sodium does, then hydrogen will win the tug of war, and it will get the electron pair, and it will have an oxidation number of negative 1. Okay, so it's based on the electronegativity. Similarly, in a similar way, oxygen. Oxygen will have an oxidation number of negative 1 when it's in peroxides, like hydrogen peroxide or lithium peroxide. Okay, so when it's in a peroxide, because that's where there's double bonds, oxygen will have an electronegativity of negative 1 instead of negative 2, and it's because of those double bonds. And then oxygen is the third exception as well. Oxygen will have an oxidation number of positive 2 whenever it is in a compound with fluorine. So OF2. Oxygen will have an oxidation number of positive 2, and that's because fluorine has a higher electronegativity than oxygen. It is the only element on the periodic table that has a higher electronegativity than oxygen. So the only time oxygen doesn't win in that tug of war is when it's in with fluorine. Okay, so when it's with fluorine, it'll be positive 2. If it's in a double bond, it'll be negative 1. And every other time, it will be negative 2. Okay, so what do you do then to figure out the oxidation numbers? So first, you assign the ones you know, and we're going to run out of time here, but like if we look at CH4 as an example, and we don't know what C is, we know that 4 has a lower electronegativity than C, so 4 is going to be positive 1. So we would say, okay, we don't know what C is, it's X, and there's 4 H's, and H is positive 1. And the overall charge on this compound is 0. And now we solve for X. X plus 4 equals 0. X should equal negative 4. we'll come back and talk a little